Okay, welcome back everybody to our 100th anniversary distinguished alumni colloquium series. Today we are very pleased to welcome Letizia Stanghellini, who received her PhD from the University of Illinois in 1995, working with Jim Kaler, and I believe that was Jim's last PhD student on planetary nebulae. And since then, she was at Bologna Observatory for a while, and ESA before joining NOAO, which is now NSF's OIR lab in 2004. Letizia works on infrared, optical, and UV imaging and spectroscopy of planetary nebulae and H2 regions in nearby galaxies. And is the head of the US National Gemini office at NOIRlab. Today, she's going to be telling us about the chemical evolution of star-forming galaxies using H2 regions and planetary nebulae as tracers. So go ahead and take it away, please.
Thank you very much. It's a pleasure to be there or here, and it has been well, I started graduate school exactly 35 years ago, and it seems like a lifetime, and school was very hard for me. When I arrived in Illinois, I might as well be landed on the moon. I didn't know the language, everything was different, but I loved astronomy and I loved stellar evolution, and eventually I think it loved me back. And so here I am, still working on stellar evolution, planetary nebulae. But in particular, my talk today will be more on chemical evolution of star-forming galaxies. This is a topic that I've developed recently because it's sort of involved a lot of other things that I've been interested about during my career. And at this point, I can use planetary nebulae also to constrain the models of star-forming galaxies. So I will start with some background for my talk. What is the motivation of this, the interest of this subject? I think is extremely interesting. I will try to go through the motivation with some time before landing on the work that I contributed personally to constrain these models. And then finally, I will have a couple of slides on future plans, which includes also some dreams. Hopefully they will come true, of what I would like to do in the future with the future instrumentation, current and future instrumentation. Before I start, I would like to thank my collaborators. In particular, Dick Shaw. Dick Shaw is also a University of Illinois alumnus, and he's also graduated with Jim Kaler, so he's my academic brother, except I only met him after graduate school when we were both at STSCI, and we started a 20-year long lasting collaboration, very fruitful. So I think that this is a good talk to mention him and thank him for all his collaboration and friendship, and also many others of my collaborators in different parts of, especially Europe, because I collaborate and I take advantage and I go back and I see Europe. So for the background, I will talk about chemical evolution of star-forming galaxies. I will talk about the origin and evolution of radial metallistic gradients. So radial metallistic gradients will be the core of my talk, constraining gradients and their evolution, and also talking about emission-line probes and how to use them with direct and strong line abundances. So my first slide of the background is my simplified view, cartoonish view of the evolution of metals in the universe, no less. So the universe starts chemically simple, as all you know, and evolves into chemical complexity thanks to the evolution of galaxies and stars. The metallicity of galaxy, really, it's very important because it carries the signature of the chemical history and through cosmic time. Star formation, for what we are concerned here, goes through two major channels, which are low mass and high mass, where the separation is about 8 solar masses. We are interested in feedback here. We are interested in gaseous and dust remnants, and not so much in the stellar remnants. So the remnants produce feedback in the interstellar medium and produce the second generation of stars and their chemistry. The two channels are responsible for the enrichment in different sets of elements. So there are two different avenues. How does the makeup of the metals in the galaxy changes? Certainly from gas accretion at the beginning, but also during the evolution. There might be subsequent inflows or outflow episodes, and also migration of stellar population might change the final makeup. So what is a radial metallistic gradient in a typical star-forming galaxy? And this is just not because I assume you don't know, but just to make sure that we are on the same page. This is a nice face-on galaxy. This is what I used to call radial metallistic gradient. So you take a metallicity, the indicator, for example, oxygen over hydrogen, you measure it in different sources or average over annually or something like that. And then you note that abundance averaged at the distance of the probe, and then you interpolate the results. Typically linearly interpolated, it can be also in other ways. And the slope of that line, assuming that is a line in the log scale, is the gradient. So from now on, I will just talk about gradients, and I mean radial metallistic gradients. And that's measured in dex per kiloparsec in general. And it is a very important constraint on the chemical evolution models of galaxies. So in the recent years, the evolutionary models have been taken into account the whole cosmology. They make a cosmological model, and the galaxy form and evolve. And then they measure from the models their metallistic gradients at different cosmic times. So for example, in the plot that I show here, I have variation of radial metallistic gradient against redshift, going from right to left, because the cosmic time goes from left to right, obviously. And this particular plot represents the model of Gibson et al. 2013, but different authors show similar results. Models show that star-forming galaxies have natural negative gradients during their evolution. By natural, I mean with some assumptions in the models, which I'm not going to go through because it's absolutely not my field and might say something that is not true. But what I read in their papers is that basically they generally assume feedback for galaxies, and they do a regular evolution following cosmology, and they obtain negative gradients. So if you include a very intense accretion on the galaxies, then you get the gradients may become 0 or even slightly positive. But I don't know if you can see my arrow here. Can you? Well, if you can, it's fine. Otherwise,
yes, I can see it.
Thank you. So the upper branch of models, this one that is close to the 0 line, those are the regular models, cosmological models of gradient evolution without enhanced feedback, which means just with a normal feedback. The lower branch of models are the models with enhanced feedback. So those two are very different. And unfortunately or fortunately, we cannot define ab initio, how nature goes. So we cannot know what was the cosmological evolution, if it was in one branch or in both or in either. so we need constraints. We need metallicity gradient constraints to see how nature goes. And before I go to the next slide, let me put this little scheme. Since I'm not a cosmologist, it took me a while to understand that the time of a stellar population goes in the same direction of redshift, and it can be called look back time, but you're looking back into the evolution of metals of the galaxy and of the universe, while the cosmic time goes opposite of redshift. And here I've assumed a standard cosmology, which is generally the case. And for this application, it doesn't really matter very much.
So Letizia, before you go on, I have a dumb question. So just to make sure I get the definition right, on these gradients, for the gradient to be negative, that's like the example you showed in the last slide. That's the sort of common thing where there's high metallicity at the center of the galaxy and lower as it moves out. That's how it's defined.
Yes. So this y-axis is actually the evolution of the gradient. So
right.
Yes, that's exactly it. The gradient is negative when the metallicity is higher at the center of the galaxy and is lower at the periphery.
Right, I see. And so for it to be flat or near zero, like you said, then it would have to be uniform throughout the galaxy. Right?
Yes.
Yeah, got it. Thank you.
Thank you. So what makes a good constraint for chemical evolutionary models? So we need to constrain gradients, and we need to constrain their evolution, because constraining gradients is not enough for cosmology. Cosmology goes from 0 to 13.6 gigayears, so we need to constrain more than just today. So how do you constrain gradients? You need a metallicity indicator where you are sure that you can get a good abundance measurement, low uncertainty, and then of course this is relative, but you have to strive to get that. You might want to get multiple metallicity indicators. Here today I'm going to talk about emission-line probes, but you can do that with stars, of course. And in general, the stellar astronomers use iron as an indicator, and we will see later what we'll use in detail for emission-line probes, but I anticipate it is gas phase, oxygen or neon or argon or an alpha element abundance. You have to be able to measure the distance from the galactic center. You are to be able to deproject if it's not face on. You need the uncertainty on the distances are severe for planetary nebulae, and we will talk about that. And how do you get gradient evolution? You can get from population of different ages in the same galaxy. For example, in local galaxy, Milky Way, M33, and so on. You need to have a good dating of the progenitor formation. Or you can go back and at different redshifts and get a young population gradient, typically H2 regions. So emission-line gas probes are really the best for this type of study because they're measurable at z equals 0 and also at higher redshifts. They make an excellent constraint for gradients and their evolution. So that's what we will talk about. It's worth noting that when you measure a galaxy gradient at z larger than 0, you're not sure that it's the same type of galaxy that you observe nowadays in the vicinity of our galaxy. But you know, that's the first step, and then you go and study the type of galaxy. Hopefully you can get this measurement in a bunch of different types. As for emission-line probes, what are the progenitors of emission-line probes? We have said that we need to date the progenitor, but how do we date them? Well, for mass, so the type of stars in the universe that produce observable gradients are either the one larger than 8 solar masses, and they produce H2 regions and excited by the massive stars. H2 regions really are T star equals 0, basically. Z equals 0 in our own galaxy. If you go at different redshift, they trace the redshift of the galaxy. If you go to planetary nebula, if you go to planetary nebula, their initial mass is 0.85 to 8, more or less. And that means that you are probing all that range of mass, which implies that you're probe around a large range of stellar times and as a consequence of cosmic times. Below 0.85 solar masses, you do not produce emission lines, so emission line probes, so no worry about that. How do you date planetary nebula progenitor? This is not easy. So from observations, populations of planetary nebula have been indicated by Jim Kaler and by other people in the past, the Pemberts, Perinotto more recently. And basically, the class of type 1, 2, and 3 planetary nebulae determine three very different mass ranges. The type 1 PN have basically the same time constraint that the H2 regions. So they're not useful to probe older population, but type 2 and 3 can be pretty old. And here I use the fuel consumption theorem from Maraston to determine the redshift with the standard cosmology of the planetary nebulae of type 1, 2, and 3. The emission line probes mark the metallicity, but you cannot measure iron. And this is something that, I mean, planetary nebulae in the galaxy, for example, they've been, their abundances have been measured for many elements, but you cannot measure iron easily because iron is locked in the dust grains. So no iron, we use oxygen. And in order to use oxygen, we need to make sure that the zero order is invariant in the AGB evolution. Otherwise, that is not a good constraint. And also that there is not significant radial migration in cosmic time, because those stars are old. If they migrate, they're going to flatten your gradients and you don't understand anymore what's going on. Well, for the first, we are pretty sure that if you are sure that, you can never be sure, but if you assume that the PN evolution comes from the AGB, and it comes either for binary or single stars, unless it's common envelope, it comes from the AGB. It's pretty safe to assume. About radial migration, as far as I know, it has not been proven that radial migration is more than 1 or 2 kiloparsecs radially, and that should not affect the gradients at this level of at this coarse level. It might be, I mean, this is the state of the art right now, but it's something to keep in mind. And also for emission line probes, direct abundances are the ones that measure electron temperature. Electron temperature needs very weak lines. And here I show the diagnostic line in a planetary nebula in M81. And that's as far as it goes, basically. For everything farther, or fainter, you have to go to H2, you have to go to strong line abundances. Strong line abundances are indexes that are calibrated based on direct abundances. So they're more uncertain, of course, but that's what we have available, and we use that. And now, as the final slide of my intro, I show you again the same plot that I showed you before of radial metallistic gradient from oxygen versus redshift. Those are all oxygen gradients available in the literature observed, and it's a nice review that I was about to do this plot, but Curti et al. published it already, so it's great. It's all there. And there are a lot of constraints that we can see here. The Milky Way and the local galaxies show pretty flat gradients in general, near zero, negative. Magrini et al., which is my collaborator, have shown that in several nearby galaxies. And at z equal around 2, you start to have a few observations. You don't resolve the populations anymore yet with the current technology. And you can have either pretty flat gradient, slightly positive or flat, and extremely negative gradients, and that's the other branch that you see. But they're both populated by lensed galaxies. Now, yes, you start to resolve population, but you know, it gets pretty tricky. And then at z equal 3, you have that fabulous result by Troncoso et al. 2014. But again, those are those are gradients that are based on 2 points instead of like 200. So, I mean, you have to put everything into context. But the 2020 scenario is that the observations seem to favor the inside-out enhanced feedback scenario without with enhanced feedback scenario. Sorry. It is worth noting that the only emission-line probe that look back in time is our planetary nebula. And here, those 3 yellow points, which are hardly seen in the plot, but are there, are our own results from the galaxy of 2018. And so, I mean, those are, they're pretty well measured, and they're local objects. They're at most 10 kiloparsecs or 15 kiloparsecs. So we know what they are, where they are, and they're all direct abundances. So,
Letizia.
yes.
So of course the planetary nebulae are only visible for a short period of time, but their abundances are really kind of telling you about the abundance when the star formed, right?
The abundance of the element that does not change with the AGB evolution. Right. Because if you go to carbon or nitrogen, you cannot do that, because that is dredge up, hot bottom burning, completely different. But those are very useful to date the progenitor, while the oxygen, neon, argon are useful to date. They basically didn't change since when the original star formed, which could be pretty far away in time because they are very old. They can be 8 giga-year-old.
Mm-hmm. So this is then telling you about the conditions in the galaxy well before the redshift at which it's plotted here.
Which could be comparable to a galaxy that is identical to ours, but of course we don't know. You know, it's a field in development. Let me talk a little bit about, see here, I completely lost my time, but maybe if you, at some point, if you tell me you have only 10 minutes, because I cannot see the time in this presenter view.
You're fine, yes.
Anyway, I'm talking about some of my results. I work on planetary nebulae for 40 years almost. And so I have a lot of results, but I'm only showing the ones that are relative to gradients, of course. This is a very nice program that we did with Laura Magrini and Eva Villaver here because I'm in Arizona at Mount Hopkins. Fabulous observatories, the MMT, horrible road. I mean, driving there is a nightmare, but we did it. And this is an exquisite match between the scientific and technical experiment, because this is M33. There you have all the planetary nebulae and that are reachable with the 6 meter and all the H2 regions. And you do that in one shot, same night, same reduction, same everything. So the difference between the 2 gradients, it's the difference between the 2 gradients. There is nothing else here. We did find type 1 and 2 PN. So let's do the type 1. We set them aside because, as we have said, they are very young and they're basically the same thing than the H2 regions. But we did find the evolution of the gradients between the type 2 and the H2 regions. And it's very, very small, very shallow, minimal, but is there and is larger than the uncertainties. A similar experiment has been done with M81, and that is, I think, as far as we can go with this. This was on top of Mauna Kea. I went and I observed with GMOS, and when you still observe on site, it was great. We found a lot of type 2 planetary nebulae, and we got the gradient, and we compared with the H2 regions. The H regions were also from MNT, so this is not exactly the same observations. And we find that the gradients of the young population is about twice the gradient of the old population, which means that the gradients are steepening with time since galaxy formation. So same result. And here is a review by Bresolin et al. By Bresolin 2017. when he put all and only the galaxies that have gradients from different populations that are from direct measurements. So with with the electron temperature. And those are all and only M31, the two that we observed, and NGC 300. And he added here, because his own work, he added the stars, I mean, giant stars, OB stars to the mix. And he found that basically in all cases, the gradients are steepening with time since galaxy formation. And so it's all and only. So whatever this means is something that is seen in all galaxies that have been observed by different authors. By doing all these metallicities in a large sample of targets in a galaxy, we can also get the enrichment, and this lower plot is from Agrini et al. And we show that there is oxygen enrichment in all these galaxies. This is an aside, but it's a nice result. And then, since I work on galactic planetary nebulae most of my life, in 2010, with Misha, we decided to do the same with galactic planetary nebulae. In this case, we divided into type 1, 2, and 3. And of course, we have big samples for each one because we have hundreds of planetary nebulae. And we observe oxygen, and we found a steepening of gradient with time again. And those 3 points that you see here, 1, 2, 3, are these yellow points in Curti et al. Plot. We eliminate from this sample the bulge and the halo planetary nebulae. We select a pure disk population. So it's pretty good. We also eliminate that we have morphology for most of planetary nebulae in the galaxy. And we know that bipolar morphology is, it can be from a different evolutionary channel, for example, binary star, common envelope, close binary common envelope. So we eliminate those and we add those, and it doesn't make a difference. It's only 8% of the sample. We still find the same steepening with time. Also, bipolar morphology is tricky to get their diameter. You can get a photometric diameter, but not a geometric diameter. The diameter is used in the statistical distance scale to get the distances. So by eliminating bipolar, we also eliminate one of the problems with the distances. It doesn't make a difference. But the thing that bugged me was that there are now about 2,500 PN in the galaxy, but 10% of them are unresolved. So you know from the spectra they are planetary nebulae, but you don't know their size. So you don't know their distance. So you eliminate in these kind of studies. That's a pretty big, I mean, if you observe an external galaxy, in any external galaxy, planetary nebulae are point sources, including the Magellanic Clouds. The Magellanic Clouds can be maybe 1 arcsecond, but it's mostly below 0.5 arcseconds. In every other galaxy that I've shown you, there are point sources. So by eliminating all these point sources in the galaxy, you're doing a big selection. So since I was studying anyway, and this is a work with Dick Shaw, I was studying anyway the compact planetary nebulae, because we observed them with Spitzer, which couldn't observe extended object in this way. And so we decided to measure the diameter of HST images of compact planetary nebulae and include them in the sample. So we observed with WIF3 several, I think it was 150 or 200 galactic planetary nebulae that are point sources, and we include them. And by the way that I was improving the sample, I also developed another way to separate old and young planetary nebula progenitors, because by working with the Star Evolution group in Rome, I realized from this plot, I mean, this plot shows the late pass of the late emission on the AGB of the external layers of the planetary nebula, and the plots nitrogen, of AGB stars, and the plots nitrogen over oxygen. And those should be directly comparable with the abundance of planetary nebulae. If you see this plot and you see that the initial abundance, the initial metallicity of the star can be, I mean, the models are run for, the models are the color one, they run for a broad range of metallicity. I mean, if you have a planetary nebula in this triangle here, you can be pretty sure that is, I mean, it belongs to, the mass goes in this direction in the models. You can be pretty sure that its progenitor is younger than 1 gigayear. If your PN has abundances in this triangle, you can be pretty sure that your progenitor, that its progenitor is larger than 7.5 years. So with this plot, with this diagram and the abundances of planetary nebulae from nitrogen and oxygen, which are really easily available from optical spectroscopy, you can determine whether planetary nebula is less than 1 gigayear or older than 7 gigayear. So we define these two groups, OPPN, old progenitor planetary nebula, and YPPN, young progenitor. And we measure the gradients with the inclusion of all the compact planetary nebulae. And this has been published in 2018, and we get a pretty big step between the two gradients, which has been confirmed, and also it has increased in the latest results, which include Gaia distances. So this is a nice result, I think. Unfortunately, I cannot see my time, but I keep going, and hopefully is not, I think I've talked for about half an hour.
Yeah, that's about right. Yeah, there's no rush.
Yeah. Okay, so something that I mentioned before, if we had carbon abundance for these PNs, then we will really be able to nail the time, the progenitor, because carbon, so carbon in planetary nebula, carbon in AGB stars, if you are below 1 solar mass or thereof, or thereabout, you never get carbon in the surface, at the surface, because you don't have the third Radial, basically. If you go between, but the actual mass depends on the initial metallicity, but let's say you go between 1.2 and 3, and then you get the carbon star. Carbon star has a lot of carbon, and that's what you observe. But if you go above about 3, it could be 4 in some metallicity, then you get hot bottom burning, and then will make your carbon become nucleosynthesized into nitrogen, big time, so 10 times. And so if you have high nitrogen, you're pretty sure that you have very high progenitor. But if the nitrogen is just slightly high, it could be a very low mass progenitor. So carbon is very important, but carbon is very hard to get, because for planetary nebula in the galaxy, the lines for carbon transitions are in the UV. And basically there is only HST, maybe the WIF3 that can observe carbon lines. So 2 years ago, again with Dick Shaw, we decided to put there a proposal, and we got 75 orbits. Unfortunately, there were snaps, and so only 30 were executed, but we got 14 very good carbon spectra. And I don't know if you can see here, this is a slitless spectrum, almost slitless spectrum for each PN. Here there are a few cases where for each emission line, you can see the footprint, also of the morphology, you can see everything. We got carbon for this sample, and we found with the same type of plots from the stellar evolution people, we found a nice small, unfortunately, group of PN whose progenitors are definitely in the 1.2 solar mass range. And those will be very useful to constrain the gradient. Of course, there are only 5. They're all far, so they're very good. They're very good probes. We'll see what, we're still in preparation. We finished the data reduction, and we see what we'll get from that sample. In the meantime, so I think my second paper was Kahn, Keller, and Stanghellini in 1982, or was it my first paper? I'm not sure. That was a paper on calibrating the distance scale for galactic planetary nebula. It's basically the Slosky scale, which myself and Dick Shaw have recalibrated in 2008 with HST data. getting an improved calibration. I mean, the more you observe, the better calibration you have. Basically, you only know, before Gaia, let's say, you only knew parallaxes and distances for 10 planetary nebulae in the galaxy, and they are about 3,000, 2050. So it's not useful for any study, any standard, any absolute candor study. With this kind of calibrations, what you do is you plot one, you find a correlation between a distance-dependent parameter versus a distance-independent parameter for a bunch of planetary nebulae that you can use as calibrators, for which you know the distance. And then you can get a correlation and get the relative distance scale. Now, when Gaia, DR1 didn't produce many parallaxes for planetary nebulae. Okay, so you cannot observe planetary nebulae with Gaia, but you observe their central stars. When you are pretty sure that they are actually their central stars, then you can get a parallax, and that parallax, if it has an error, an uncertainty that is less than 20%, you can use to calibrate the distance scale. And in this plot, I show our paper from last year, where we recalibrate the distance scale, and those are all Gaia parallaxes with uncertainties less than 20%. And we found the scale here in the blue box, which is basically, if you measure the surface brightness of a planetary nebula in H beta, which means you measure its flux and its size, then you have its physical radius. And from the physical radius, and again, the apparent radius, you get the distance. And this scale is better than any other scale, including my scale, including Canetal scale. It's better not by much, but by a little. But we are really studying already the DR3. And in the DR3, we have many more parallaxes. So why don't we use directly the parallaxes for the gradients? We can't, because the parallaxes only go to 3,000 parsecs or something like that. So they really let us midway, and they're not useful, but they're useful as calibrators. So I did, I think 2 days ago, I recalculate the gradients, the Stanghellini and HII gradients for the DR2 distance scale. I never done that before, and I found steepening of gradients with time, more or less the same gradients. It didn't change very much. It changed a little bit, going again into the right direction, the direction I think that's where nature is going. Although I would be happy if there was the opposite direction, it would be probably even more exciting. And so we are already working in DR2. After I did this gradient for the young population, a friend of mine that is part of the apogee group told me, oh, that's identical to the young stellar clusters in the galaxy. And in fact, there is this paper by Donor et al. That show that the apogee gradient for young clusters, exactly in the same age domain of the young planetary nebula progenitor, is 0.02 dex per kiloparsec. That's good. Oxygen, of course. Okay. So if there are not questions, I think I'll go to the future. Let me get a sip of water. So this world of metallistic gradients is very exciting. It gave me a chance to study a little bit of cosmology, which I hadn't studied much in my life because I worked on the galaxy and on the Magellanic Clouds. And it opened up a lot of interesting projects to be done. And of course, the next big thing is JWST. And I couldn't be happier that I am one of the many co-Is of a very important program in Cycle 1, which will observe spectra of UDF galaxies. So UDF is the ultra deep field with HST, and is a survey of galaxies. And this project is, I will only say as much as is in the public information, of course, but it's a near NSA spectra used in such a way that we create IFU-like maps of galaxies and will achieve spatial resolution. I think this will be the first time in which redshifted galaxies will achieve spatial resolution, of course, with other programs of the JWST. But the interesting thing for me is that if you go between 2.5 and 3.5 in redshift, then you'll have all the diagnostic lines for planetary nebulae and H2 regions. Sorry, forget planetary nebulae. We will not observe directly planetary nebulae. For H2 regions, they will fall into the observations. So we will be able to do strong line abundances and gradients for a lot of galaxies, a few dozens of galaxies in this range of redshifts with resolved stellar populations, with resolved H2 regions. So if you see, this is another of these plots that where redshift or look back time is plotted, sorry, where gradients are plotted against the look back time. It's actually backward in redshift from the previous ones, because I think this shows better what I want to say here. So redshift goes from left to right together with the age or look back time, while the age of the universe, the cosmic age, goes right to left. Here there are the two branches of models, the upper branch with enhanced feedback, which is the one that seems more constrained from the observations, and the lower branch is the branch without enhanced feedback, which is constrained by now only by a few lens galaxies. These points, the square is the H2 regions in the galaxy gradient. The two dots, black dots, are M33, the two gradients from planetary nebula and the H2 regions. The blue dot is planetary nebula in M81. I'm just reviewing all the things that I've showed you. And the two red dots are the last experiment of gradients for galactic planetary nebulae with abundances from Stanghellini and HII 2018, Gaia distances, Gaia distance scale, and young and old planetary nebula progenitors. Those really, I mean, if I have put any of the earlier results, it wouldn't have changed very much. But the latest results make me more confident that that works, because I really think that now we have two samples of different ages of planetary nebula. I also plot the AMAZE, the massive, and other surveys here, and where their gradients fall. So most of them fall in the upper part of the plot, which means that the gradients are steepening with time. The Wong et al. Sample fall in all this range, so it's not conclusive, but again, it's only lens galaxies. So with this green green rectangle here, this is the domain of the JWST gradients, we'll really be able to determine whether nature is choosing this branch, or maybe both, or maybe something in between, we don't know. We'll try to reduce the data to get excellent data and reduce the data very well, and to make sure that we have a constraint, and this is very exciting. Let me see if I have said everything about this. Yes, okay. And finally, this is basically future. I don't know if this future will involve me, because I don't know when the extremely large telescopes will be operating, but I've done some work with the WFOS group to get some exemplary proposals, things that can be done with the ELTs. This in particular is with the MOS on the TMT, but a MOS in the GMT will work as well. We can do direct abundances of nearby galaxies for a lot of galaxies, and for planetary nebulae in a lot of galaxies. In the 10 megaparsec volume, we can do the experiments that we have done for M33 or better in 15, 20 galaxies. And in this case, we can do the H2 region analysis completely from the 8-meter class telescopes. So we will not use ELT time, but we will need a ELT to get direct abundances for the planetary nebula. By direct, I mean observing the 4363 or other diagnostic lines at that level of flux that I showed at the beginning. But even most important, we can go into the Virgo cluster with the ELTs. With that means that we will have not 2 or 3 or a dozen galaxies, we will have a bunch of galaxies where we can do this experiment. Only 25 reachable by the north. Similar studies could be done from the south, for example, using the GMT. And in this case, with one pointing, we can probably do the gradients of both PN and H2 regions together. So that will be the best way to do these gradients. Those will be local gradients, but as you recall, the PN will give you the redshift, but at this point will be in the same galaxy. And by observing dozens of galaxies, we will have that component, which is mass of the galaxy, morphology of the galaxy difference, and we can have the gradients, evolution in all those different type of galaxies. Here is my time estimate for the TMT. It can be done pretty easily in the 30-meter class telescope. I think I am almost at the end. Just that my summary. I hope I explain and convince you that there is purpose in pursuing the radial metallistic gradients. That is, it's fun to do cosmology with planetary nebulae in the galaxy. It reminds me when they say, when you measure Zanza temperature, you do UV astronomy from the ground. It's a similar thing. You can just use a trick, which is fair, with some assumptions, and you can go back in time or out of the atmosphere in the case of the Zanza. So I've reviewed the work I participate in for, or I led for gradients in nearby galaxy and in the galactic gradients. My pursuit in the better and better distance scale, I think Gaia made a big difference. Also in our confidence on these distance scales, the results are not so different from previous results. I haven't done a thorough examination of the old scales with the new scale, but I think it gives us much more confidence now on using planetary nebulae. And it seems there is a consensus from the current data that gradients are steepening with time since formation of the galaxies. It should be fed back to implication, other effects that might change the gradients, and it should be related to the different type of galaxies. A lot can be done with JWST. In the program I'm on will be a part of it. There are other programs that explore gradients, as I seen from the summary webpage. And the extreme large telescopes, both in the north and the south, can open up a completely different set of parameters. And I think that this field will flourish under the extremely large telescopes. And thank you very much.
Thank you, Letizia. Do we have any questions for Letizia? Yes. Oh, I see you clapping. Good. Yes. Any questions? Yes, Brian.
Yeah, so Letizia, thanks for your talk. So I'm sorry Jim couldn't be here because he would have enjoyed it very much. So a couple of things. So one, you showed a galaxy where you were looking, I think it was nitrogen and oxygen, and they had different gradients. It was two different elements and they had different gradients in the same galaxy. Am I remembering that right?
I don't think I showed different gradients for the same galaxy.
Maybe I was misunderstanding what I was seeing.
I don't think I show anything by.
You were always using oxygen. Okay.
I think so. In this talk, I think I showed only oxygen.
I think there was one maybe with nitrogen, and I was thinking maybe you saw different gradients in nitrogen and oxygen, and I was going to
use nitrogen to date here is nitrogen
okay.
also to date the progenitors. Yes.
Right. Got it. That's fine. I got it. I understand. But a different question was, so for the same galaxy, you could look at the abundance gradient that you see through the planetary nebula. You can also look for just the gradient in starlight, so just look at like if it's an exponential disk or something like that, that has a different sort of scale length and gradient to it. How do those compare?
By starlight, you mean the gradient of the density of stars?
Right.
Yeah.
So if it has like an exponential disk, that will also have some gradient with sort of similar units. How do those compare to each other? When you're able to compare?
A starlight gradient of now I don't have in my mind. I cannot. I think that I cannot. I never made this comparison. This is a very interesting question, actually. It's also especially interesting if you think about H2 regions. Planetary nebulae have, I mean, they're faint. They don't particularly go very far into exciting. I mean, they excite the ejecta, while the H2 regions come in groups. And so it might be very relevant to see how they compare with. I have now I remember that I've seen some of these, but I don't remember exactly how they compare. So I cannot answer your questions, but it made me think that maybe it might be important to see what is the difference for the group from young stellar groups, basically. And I think that JWST will go into a lot of details of stellar groups, and especially because they go through the dust, so they can really see what the young stars and young stellar objects, where they are and how do they shine without much absorption, because they go through that. I don't know if you instead have in mind how the gradients of that starlight goes, and you want to comment on that?
No. It was the most naive possible question. Yeah, no, but what you said is very interesting. So it sounds like you could then compare different measures of the evolution over time if you did it, if you compared to different, as you say, to H2 regions, and maybe and I don't know if the stellar, just the exponential character of the disk, in the density of stars, if that would also, add additional information.
I think so.
Robert.
Hi, Letizia. I was curious about the near UV observations that you had. So that was STIS. Did the setup include nitrogen 5?
Yeah. If it's there, we got it. Yes, we have 2 or 3 PNs that show nitrogen 5.
Do they tend to always be the hot star PN, or are they?
Yeah. As you see from this is just a sampler.
Yeah.
A pretty one. You see the spectra, for example. You see the nebular lines, but you also see the stellar spectrum. The line is the central star spectrum, which is very blue. We did find the temperatures for most of them from the central star spectrum, and to be totally honest, in a couple of cases, they result. This is not finished yet. The result is that they are very different from the Zanstar temperatures. I wonder if there is if we're using a wrong method to get the temperatures, but you can tell the temperature from the spectrum without measure them. And yes, in a couple of cases, but in a couple of cases, the nitrogen 5 is shows up as a P Cygni profile, which means it's probably not even you know what is a P Cygni profile is is not probably even due to direct photoionization. So it might be that the temperature, it has to be high, of course, but might not be correlating as strictly as we expect with the temperature. So we have to solve that nitrogen 5 issue, but we do see it in a few cases.
Yeah, so Yoa and I had been looking, we'd actually looked more at oxygen 6, but with fuse. But the question would be whether nitrogen 5 shows up and you can actually see the interface layer with an X-ray bubble in the center. So if the central star is cool enough, you can disentangle the effect of photoionization from the cooling line that you would get instead from the interface layer.
Are you talking about in 2D?
Yeah.
Because I have to recall that those are very tiny.
Yeah.
0.3, 0.2 arc seconds. They're compact. So the type of PNs that you have been studying are probably more extended. So you can see the interface here. And with this doesn't have a great spatial resolution. Sorry, doesn't have a great image quality for this type of things. So it might be hard.
No, I'm sure it's hard.
Yeah.
I was just curious if the data existed, actually.
Yeah.
It looks like, I think I'm seeing near nitrogen, maybe it's not nitrogen 5, in the far UV spectrum in the second, the top.
I cannot enlarge this slide because I'm in presenter view and I don't see, and I don't remember which one. I don't remember, I have no memory, so I don't remember which one was the one, but I remember that we have three or four that show nitrogen. We can, if you're interested in that, so we basically are publishing a basic observation. The reduction took forever because it's special mode. And then we did the comparison with stellar evolution in the case of single star. If you're interested in nitrogen, we basically wrote a carbon paper. If you're interested in the nitrogen 5, we can talk about it later. I can send you the few that have nitrogen 5 and we can talk.
If it's only in the stellar spectrum, I don't know whether or not it would be something that would be easy to disentangle.
No, it's also in the nebula spectrum. Yeah.
Okay. Yeah. I don't know whether I'll have time anytime soon, but actually, if you make sure Yoa knows about it,
yeah,
Yoa will probably jump on it.
Okay.
Yeah.
Thank you.
Yeah. Cool.
So I don't see any other hands, but I have a question. So it occurs to me that the behavior of the metallistic gradient with time probably is linked not just to the type of galaxy, but also its merger history. I wonder if you could comment on the interpretation of steepening or shallowing of the metallistic gradient and what it's telling us about the galaxy's history.
Yeah, absolutely. I mean, it will absolutely. So if you are, I mean, as I say many times, cosmology is not my field. So I don't want to say anything too extreme or too strange, but of course, mergers are very common, and we are talking about. So you are talking about cold mergers, or I mean.
Well, I mean, they're gas-rich mergers, gas-poor mergers. Probably produce different results too. Yes,
because I mean, if you think about it, probably for cold mergers, I mean, cold mergers that produced non-star forming galaxies or low star forming galaxies, this doesn't apply because we are talking about star forming galaxies. For spirals, well, of course, mergers will change the gradient. In general, all the catastrophic events tend to flatten the gradients. Mm-hmm. But in the case of mergers, I mean, let's say differently. This type of behavior has developed with the cosmological models, which of course involve also mergers, involves all all sorts of events that can happen in galaxy formation through the cosmological time. So in a way, those are already the results when you go and look at star-forming galaxies, whether they come from mergers or not. But I don't know if this was your question, or maybe if you can tell from a gradient that the galaxy has had a merger. You can tell from a gradient. I mean, let's suppose you have two identical galaxies and you can observe two identical galaxies. And one gradient is steeper than the other, just not evolution, just two gradients at today's time. Then you can tell that the steeper one is because the galaxy is in a group, or because the galaxy has had an event that has steepened the gradient. And we have done that actually. We have observed analogs of M33 and also of the Milky Way to see if getting identical galaxies, one in a group and one isolated, will make a difference in the gradients. Unfortunately, we were not able to get the gradients in enough detail for, I think it was 45, 46, or 46, 45. There's one nearby galaxy that is really very close to a Milky Way analog, but is in isolation. And then we compare also M81, which is in a group, in a tighter group than the galaxy, to see if there was a difference. And the gradients of M81 are steeper. One of the conclusions of the paper was that that is because it's in a group. But then I read in the immense literature of gradients, I've read a paper, I don't remember the author though, that says that if you have a galaxy in a group, the gradient is flatter because previous mergers may have flattened the gradient. So I don't know, I cannot give you a scholarly answer to this because I don't know enough, to be honest.
Okay. It seems like, yeah, you should be able to plot maybe the gradient magnitude versus local density, right? Measure of local density like is used in merging rates and things like that, and maybe see some kind of evidence for a trend.
Yes.
Yeah.
Yes, you could. This is really the zeroth order of comparison, but you could do much more, especially if you had a lot of galaxies that for which you do the same type of observations and you can actually compare them directly. That's the difficult thing.
So with a 30-meter telescope, how far out could you see the H2 regions? I'm assuming that the planetary nebula are not a limiting factor.
Well, the slide that I show is for direct abundances. For direct abundances, you only do, I mean, this is the different type of doing evolution of the gradients with planetary nebula and H2 regions. For that, you can do up to, I mean, Virgo, a little farther, so not very far, local galaxies, basically. But that's okay, because if you can get, I mean, right now, we can only do that in 2 galaxies, 3 galaxies, and not very well. But, and so we cannot really compare because we only have 3 galaxies. We cannot really put them in groups or in classes or things like that. When we will be able to do it with Virgo, in a night of observation, we do all of them. That will make a difference because at that point we know, I mean, how do those gradients go with mass, with possible merging history, with, as you just, this ring the bell, and other parameters. So that is what I was thinking for the ELT. For the ELT going back in redshift with this type of work, I'm sure you can do it with strong line abundances for H2 regions. But I think really the best application for this kind of science is local group, many, many galaxies, a lot of planetary nebula, a lot of H2 regions. And you go back in time within the same galaxy with stellar populations.
Right.
So.
Cool. Very good. So if there are any further questions, going once, going twice. Okay, let's thank Letizia again for giving a great talk, and I guess that'll be it. Thank you very much.
Thank you very much for having me.